A couple of months ago, I made a video about the probability of getting a triangle by breaking a stick at 2 points. And it was actually the very first video of this YouTube channel. And a couple of weeks ago, one of you actually asked me what would be the probability in the case of not any triangle, but an acute triangle. So to summarize the previous video, we were assuming that we were having a stick of length 1, and we were randomly breaking the stick at 2 points on this 0, 1 segment, so a point that we will call X and a point that we will call Y. And by breaking the stick this way, we were obtaining 3 small sticks of length X, Y minus X, and 1 minus Y. And then we were using the fact that 3 sticks of length A, B, and C could only form a triangle if we have A plus B is lower or equal than C. And by using this condition and showing graphically all the possible value for X and Y, we were able to show that the solution space in which we were getting a triangle was exactly the solution space described by this area here, where here we are in the middle of the axis X, and here we're in the middle of the axis Y. And this area is exactly equal to 1/4. So this was giving us the probability of getting a triangle by breaking a stick at 2 different points. So this was the probability of getting any type of triangle. So what about an acute triangle right now? So first, let's go back to the definition of what is an acute triangle and also what is an acute angle. So let's say that you have a triangle like this with the 3 angles alpha, beta, and gamma. We say that alpha is acute if and only if alpha is smaller than 90 degrees or pi over 2. And for a triangle, we say that a triangle T is acute if and only if the 3 angles alpha, beta, and gamma are strictly lower than pi over 2. So now what we're going to do is, from this definition of what an acute triangle is, we are going to derive a condition on the side length of the triangle. So what we're going to do is to draw another triangle that will look this way. And we are going to define the length here A, B, and C. We are going to call this angle alpha. We are going to extend this length here, and we are going to call this other angle beta. Now, from there, we are going to build a right triangle. So to build this right triangle, what we're going to do is to build a new segment that will connect this point over here and is going to be perpendicular to the side A. Now, let's focus on this triangle over here. And we can see that the hypotenuse of this right triangle is equal to B, and this angle here is equal to beta. So according to trigonometry formula, we know that this length is equal to B cosine of beta, and this length over here is equal to B sine of beta. Now let's take a look at this other right triangle over there. And according to the Pythagorean theorem, we know that C squared is equal to B sine beta square plus A plus B cosine beta square. By developing, we find B square sine square of beta plus A square plus 2AB cosine beta plus B square cosine square of beta. This is equal to A square plus 2AB cosine of beta plus B square cosine square of beta plus sine square of beta. And it is a well-known identity that this sum is equal to 1, whatever the value of beta is. So we have A square plus B square plus 2AB cosine of beta. As we have seen above, the angle alpha is acute if and only if alpha is strictly lower than pi over 2. but we have beta that is equal to pi minus alpha. So we have acute if and only if beta is strictly greater than pi over 2, which is equivalent to say that cosine of beta is strictly negative. And because A and B are considered to be lengths that are positive, this is equivalent to say that 2AB cosine of beta is strictly negative, which is equivalent to say that C square is strictly lower than A square plus B square based on the formula that we just demonstrated above. So here you go. The angle alpha is acute if and only if C square is strictly lower than A square plus B square. And for an acute triangle in general, not just an acute angle, we must have this inequality for every single pair of side, which means that we need to have B square strictly lower than A square plus C square and A square strictly lower than B square plus C square. And so these three inequalities are the key conditions that are going to help us find the probability of getting an acute triangle by breaking stick at 2 points. So now one other intermediary result that I would like to show, and is going to be useful later on, is I would like to show that C square strictly lower than A square plus B square implies that C is strictly lower than A plus B. And there is actually a quick trick to prove that. The trick we are going to use is to say that if C square is strictly lower than A square plus B square, then of course we have C square that is strictly lower than A square plus B square plus 2AB. And this is because these lengths are positive. But then this implies that C square is strictly lower than A plus B square, because the formula above is the development of A plus B square. And by applying the square root on this, we have C that is strictly lower than A plus B. So this is how we demonstrate this result above. And if you think about it, it kind of makes sense because, as a reminder, this is the condition to obtain a triangle, and this is the condition to obtain an acute triangle. So this result is basically proving that if you have an acute triangle, then you are having a triangle, which is kind of trivial. And the reason why this result is interesting for us is because when we are going to plot the region in which we will be able to obtain an acute triangle, well, we know from this result that this feasible region will be contained in the region that is allowing us to have a triangle. So the feasibility region of the acute triangle that we are displaying in red will be inside this triangle region that was shown in white. So now the next step will be to use this condition that we found over here and apply them to the x and y value that represent the point where we are breaking the stick. So as a reminder, the three lengths that we are obtaining here are x, y minus x, and 1 minus y. So if we are applying these three inequality over there to the x, y minus x, and 1 minus y, we are obtaining the three inequality for y and x, which are x square is strictly lower than y minus x square plus 1 minus y square. Y minus x square is strictly lower than x square plus 1 minus y square. And finally, 1 minus y square strictly lower than x square plus y minus x square. So here I'm not going to do all the development. I will let you play with it on your own and tell me if I have made any mistake. But basically, by developing these three inequality, we end up having this new inequality, which are y is strictly lower than 1 divided by 2, 1 minus x. Y is strictly greater than 1 plus x minus 1 divided by 2, 1 minus x. And finally, x is strictly lower than y minus 1 plus 1 divided by 2y. And so, as I said above, we said that this feasible region of the acute triangle will be contained in the region of these two triangles that represent the feasibility of getting a triangle. And we are going to focus on the region where y is strictly greater than x, so that region over here. And the reason why we can focus on this region only is because by symmetry we can perfectly switch x and y. And as I was explaining above, the region of the acute triangle should be contained within that region, which means that we can basically bound this equation over here by the equation defining the region of the triangle itself. And you can see that this region is actually defined by the inequality y strictly greater than 1/2, x strictly lower than 1/2, and finally y strictly lower than 1/2 plus x. And so because the acute feasibility region is contained inside the triangle feasibility region, we know that this quantity over here is bounded by 1/2 plus x. This quantity is strictly greater than 1/2, and that quantity is strictly lower than 1/2. And that means that we can calculate the probability of getting an acute triangle by using the area of getting a triangle and subtracting from it the region that is not acute. So it will be this area over here, this area over there, and this area over here. So if we zoom a bit more on this region, we can see that this is the line of equation y equal 1/2. This is the line of equation x equal 1/2. And this is the line of equation y equal x plus 1/2. And now, thanks to the new inequality above, we just identify the line of equation y equal 1 plus x minus 1 divided by 2, 1 minus x. Then the line of equation y equal 1 divided by 2, 1 minus x. And finally, the line of equation x is equal to y minus 1 plus 1 divided by 2y. And now the goal will be to calculate the area of the region A, B, and C. And we can see that we can calculate this area by doing an integral. And we have the area A is equal to the integral from x is equal to 0 to 1/2 of 1 plus x minus 1 divided by 2, 1 minus x minus 1/2 dx. And this is because we shouldn't forget to subtract this function to calculate the integral. The area B will be equal to the integral from x equals 0 to 1/2 of the function x plus 1/2 minus the function 1 divided by 2, 1 minus x dx. And finally for C, we have to do things a bit differently because this time we are going to do the integral over the variable y from y equal 1/2 to 1 of 1/2 minus y minus 1 plus 1 over 2y dy. So let's go ahead and calculate these integrals. So for the integral a, what we're going to do is first subtract the 1/2 to the 1 that we have here. And we have the function x squared over 2 plus x over 2 plus logarithm of 1 minus x divided by 2. And this function is evaluated in x equal to 0 and 1/2. When evaluated in 1/2, we have x squared over 2 that is equal to 1/8. So this is equal to 1/8. X over 2 is equal to 1/4. So plus 1/4. And finally, the last quantity is equal to the logarithm of 1 over 2, everything divided by 2. And we know that the logarithm of 1 over 2 is equal to minus the logarithm of 2. So we have minus logarithm of 2 divided by 2. And finally, when this expression over here is evaluated in 0, we have the x squared that is equal to 0, x that is equal to 0, and logarithm of 1 minus 0, which is equal to 0. So everything is equal to 0 when evaluated in 0. So at the end, the integral a is equal to 3 divided by 8 minus the logarithm of 2 divided by 2. Now, for the integral b, before trying to calculate it, what we can notice is that this expression is exactly equal to the expression in a, and the integral is made between the same bound. So at the end, we know that the integral b is exactly equal to the integral a, and so this is also equal to 3 divided by 8 minus the logarithm of 2 divided by 2. Now, finally, for the integral c, what we are going to do before trying to calculate it is to proceed to a change of variable, and the change of variable that we are going to use is the change of variable u equal to 1 minus y, which is equivalent to say that y is equal to 1 minus u. And we notice that in that case, we have dy that is equal to minus du. So what's going to happen is that we are going to do the integral from u equal 1/2 to 0, but this is exactly like doing the integral from u equal 0 to 1/2, and the minus du will become plus du as long as we invert the bound of the integral from u equals 0 to 1/2. And so we have integral from u equals 0 to 1/2 of 1 divided by 2 minus u plus 1 divided by 2, 1 minus u du. And this is equal to the integral from u equal 0 to 1/2 of 1/2 plus u minus 1 divided by 2, 1 minus u du. And again, as you may recognize it, this is also equal to b and to a, so this is also equal to 3 divided by 8 minus logarithm of 2 divided by 2. So at the end, we just proved that the three areas that we need to subtract from this right triangle that is supposed to show the area of feasibility of any triangle, we have to subtract the area A, B, and C that are all equal to 3 divided by 8 minus logarithm of 2 divided by 2. And we shouldn't forget that we have to subtract the same three areas from the other triangle that represent the portion where y is lower than x. So by symmetry, the three areas are exactly the same and are displayed over here. So at the end, the area of feasibility of the acute triangle is equal to the area of feasibility of any triangle that we previously calculated in the previous video and is equal to 1/4 minus 1, 2, 3, 4, 5, and 6 times the area A that is also equal to the area B and C and is equal to 3 divided by 8 minus logarithm of 2 divided by 2. And so the area of feasibility of the acute triangle is equal to 1/4 minus 6 times 3 divided by 8 minus logarithm of 2 divided by 2. And this is equal to 2 divided by 8 minus 18 divided by 8 plus 6 divided by 2 logarithm of 2, which is equal to minus 16 divided by 8 plus 3 logarithm of 2. And this is equal to 3 logarithm of 2 minus 2. So at the end, the area of feasibility of the acute triangle, which is also equal to the probability itself of getting an acute triangle, because the area of the total square is equal to 1, this probability is equal to 3 times the logarithm of 2 minus 2, and this is approximately equal to 7.9%. So at the end, we showed that the probability of getting any triangle was equal to 25% exactly, and the probability of getting an acute triangle this probability is significantly lower and is exactly equal to 3 logarithm of 2 minus 2, which is approximately equal to 7.9%. And for those who would be interested to see what this area looks like in practice, well, we have an illustration right here. So as you can see, the area delimited by the dash dot represents the probability of getting any triangle, and the blue area that you can see here is actually the area representing the probability of getting an acute triangle.